more on the MCQs based on the concept of number theory. Let's take the first question. Question is, what is the remainder when this number is divided by 7? In this question, there's no need to take first power and then add it and then divide by 7. We will use the concept of congruency. In the concept of congruency, we can divide each number by 7 and find the remainder. Suppose the remainder is R1 in this case. Similarly, divide this number, find the remainder when divided by 7. Let's suppose R2, in this case R3, in this case R4. Whatever the remainder we have, add this one. If that number is greater than 7, divide again by 7 and find the final remainder. Now we are dividing by the 7 and 7 is a prime number. So in this case, we can use the Fermat's theorem, which says that if P does not divide A, then A raised to power P minus 1 is congruent to 1 mod P. For the first case, we have A is equal to 2. Whether 7 divides 2? No. So it means we can use the Fermat's little theorem and we can apply this result, and we have 2 raised to power P minus 1 is 6 is congruent to 1 mod 7. Now we need a 20 power here, but we can take the nearest number to the 20, that is a multiple of 6. How? We can increase the power both sides as a 3, then we will get 18 here. On the left side, we have 2 raised to power 18 is congruent to 1 mod 7. But we need 2 raised to power 20. In the next step, we can multiply both sides by 2 square. And on the left side, we have 2 raised to power 20, that is congruent to 2 square, that is 4. And 4 is less than 7. Therefore, we cannot further split this one. So we can say that 2 raised to power 20 when divided by 7, the remainder in this case is 4. So here we are getting R1 is equal to 4. Similarly, calculate for the next case. According to this, A is equal to 3. And 7 does not divide 3. Apply Fermat's little theorem. We have this. Then we need 30. Nearest number of 30, that is a multiple of 6. That is itself 30. So what we can do? We can take both sides as a power 5. On the left side, we have 3 raised to power 30 and on right side 1. It means when 3 raised to power 30 is divided by 7, remainder is 1. Now calculate R3. In this case, A is equal to 4 and 7 does not divide 4. Apply the Fermat's little theorem. We have 4 raised to power 6 is congruent to 1 mod 7. A number that is a multiple of 6 nearest to the 40 is 36. It means we can take both side power as the 6. From here we have 4 raised to power 36 congruent to 1 mod 7. Now we need 40. So multiply both sides by 4 raised to power 4. Now we can further split this one. There's no need to calculate the power. This is 4 into 4 into 4 into 4. Now 4 into 4 is 16. Take the remainder when divided by 7. 16 when divided by 7. Remainder is 2. Even in this case, 4 into 4 is 16. When divided by 7, remainder is 2. 2 into 2, that is 4, and 4 is less than 7. So it means we cannot divide further and the remainder final is 4. Taking the next case, A is equal to 11. Now 7 does not divide 11. So A raised to power P minus 1. It means 11 raised to power 6 is congruent to 1 mod 7. Now we need a power 7. So we can take both sides 11 in a product. On the left side we have 11 raised to power 7. On the right side 11. Now can we further divide 11 with the 7? Yes, because we will get the smallest integer in this case. 11 when divided by 7, the remainder is 4. So in this case, again we are getting a remainder as a 4. What is the sum of these 4 numbers? That is equal to 13. Now again divide by 7. So when we again divide by 7, what we have equal to 6. Hence option D is correct. So in this case, we have applied the multiple times of Fermat-Little theorem, and separately we have calculated the remainders. After that, we have taken the summation of the remainders, again divide by 7, and the last remainder we get 6. Next is, if A and B are the relatively prime numbers. Now whatever the data is given to you, directly write the result corresponding to that. Because we know that if the numbers are relatively prime integers, their GCD is 1. GCD means greatest common divisor is 1. Then what is the GCD of these three numbers? So whenever we have 0, GCD of A is 0. That is always A. Because we can write 0 as 0 into A and A as A. So what is a common divisor? A. Or we can say that whatever the GCD we have for A and B, that must divide 0. Because 0 is divisible by every non-zero number. So in this case, GCD of AB0 is equal to GCD of AB, because we can ignore 0. And what is the GCD of AB? That is equal to 1. Next, according to the division algorithm, for the given integer A and B, where B is greater than 0, then there exist a unique integers E and F with this condition such that which of the option is correct. You can observe that we have the condition on the F, and in division algorithm we have the condition on the remainders. So it is a remainder. And if it is a remainder, this is clearly quotient. Now we just need to identify which is a divisor and the dividend. As we are dividing by the B, because we say that the remainder is less than B. So we can write A is equal to quotient into divisor plus remainder. Quotient in this case is represented by E and number is divided by B plus remainder as F. So according to this, option B is correct. Next, let A, B, C are the integer where A is not is equal to 0. The first condition is if A divides B implies A divides B into C for any real number C. This statement is incorrect. Why? Because when we say that A divides B, according to this, B by A is equal to integer. And if we take the second condition, A divides B into C, that is equal to B into C by A is equal to integer. And that is only possible when this number is integer. Because from here, we are getting integer. Integer into integer is integer. So it is incorrect because of this word. If it is an integer, then the statement is true. Second, if A divides B, A is greater than 0, B is greater than 0, then A is strictly less than equal to B. Yes, because when we say A divides B, B by A. So this is only possible when A is less than equal to B. Third, if A divides B and B divides A, that is only possible when A is equal to B. No. Remember that when we say that A divides B and B divides A, that is possible in a two cases, either A is equal to B or A is equal to minus B. Take the case of 2 and minus 2. 2 divides minus 2, minus 2 divides 2, but both are not equal. So it satisfies this condition. So it means third is incorrect. Fourth, A divides B, A divides C, then A divides their linear combination for any integer x and y. Now the statement is clearly correct. Hence option A is correct. Next, every integer greater than 1 can be written uniquely as a prime, or the product of two or more prime is the statement of. So this statement is for the fundamental theorem of the arithmetic. Next, let A is an even number and divisible by 8. Then what are the possible remainders in a A square? Whenever we have such case, A number is given to you, but we need to find the remainder for their square or a cube. What we can do, we will check with which we are going to divide the number. That is 8. So it means every number can be written in the form of 8k plus 0 because the remainder is 0, or 8k plus 1 whose remainder is 1, 8k plus 2 whose remainder is 2, 8k plus 3 whose remainder is 3, and same for the other till 7. Why? Because the last remainder possible in this case is a 7. Now, as per the question, we need to take the even number. Even number is this, 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 and this. Now, if we take the square of such number, what is the square of this number? That is the 64k square. When divided by 8, what is the remainder in this case? That is exactly divisible by 8 because of this. So, hence 0 is one possible remainder. In the case of this, it is a 8k whole square plus 2 times of 8k into 2 plus 2 square. When you divide by 8, this number is exactly divisible by 8. This is also divisible by 8. It means in these two cases, the remainder is 0. Whereas 2 square is not divisible by 8. And final remainder we are getting in this case is 4. For the next case, 8k plus 4. Take the square of this number, that is equal to 8k whole square plus 2 times of 8k into 4 plus 4 square. This number is exactly divisible by 8. This is also divisible by 8. 4 square is 16. That is also divisible by 8. So remainder in this case is 0. Calculate the next case. 8k whole square plus 2 times of 8k into 6 plus 6 square. Exactly divisible by 8. Exactly divisible by 8. 6 square is 36. When divided by 8, remainder is 4. So it means we are getting only a two possible remainders, that is 0 and 4. Note that in these forms, k represents the integer. So do not get confused whether this number is exactly divisible by 8 or not. That is surely divisible by 8 because we are taking k as an integer. Next is the number of solution of this congruence in Z18 is equal to what? We need to find the number of solution, not the solution, means x. How to find that? First we will find the GCD of these two numbers. First, subtract 48 in a prime factorization. This is 2 into 24. 24 is further subtracted as 2 into 12. 12 is further subtracted as 2 into 6. And 6 is 2 into 3. Whereas 18 is 2 into 9 and 9 is 3 into 3. What are the common integers we are getting in this case? That is 2 and 3. So GCD of 48 and 18 is equal to 2 into 3 is equal to 6. Now check whether 6 divides 12. It means 12 by 6 is equal to some integer. Yes. It means it has a solution. Now how many solutions? That is equal to the GCD of these two numbers. Hence option A is correct. If x is a common solution of these congruents, then this is equal to what? Do not apply directly Chinese remainder theorem by observing the system of linear equation, system of linear congruency. Think as per the statement, we have x is congruent to 3 mod 4 and second is x is congruent to 3 mod 5. We need to find a common integer x such that when divided by 4 remainder is 3 and when divided by 5 remainder is again 3. Let's take a remainder 3 itself. So here we have direct value, that is 3. Because x is equal to 3 is applicable in both the cases. Now if we have x is equal to 3, when divided by 5, what is the remainder? 2. But it says that 1. So that means A is incorrect. When divided by 9, it is not divisible by 9. So hence remainder is 3. Hence B is incorrect. 13, not divisible by 13. When divided by 2, remainder is 1. Hence option D is correct. Next is the smallest value of x which satisfies these congruency. Again, do not apply directly Chinese remainder theorem. We will pick the option, check which one is satisfying this one. Check for the 14. 14 when divided by 5, what is the remainder? Remainder is equal to 4. What we need? 3. It means 14 is not the solution of the system. For 28, the 28 when divided by 5, remainder is 3. And even we need as a 3. Let's check it whether it is satisfying in this case or not. 28 when divided by 6. What is the remainder? This is 6 into 4, 24. Remainder is 4. It means 28 is satisfying both the equation. Hence, that is the final answer. Even we need a smallest value. After that, we are getting a greatest number to the 28. So, there is no need to check in that case. Next is, what is the multiple inverse of 7 in Z12? What do you mean by multiple inverse? Simply, we just need to identify 7 is multiplied with which number that is congruent to 1 mod 12. Because Z12 indicates that we are dividing by the 12. We need the inverse of 7 means we need to product with 7 and it should be 1. There is no need to simplify this with the help of Euclidean algorithm or a Bezout's lemma because direct options are there. Just check it when we plug x is equal to 1, whether the remainder is 1 when divided by 12, that is equal to 7, not 1. So it means it is not the correct answer. X is equal to 5. 7 into 5 is equal to 35. When divided by 12, remainder is equal to what? That is 11. Hence, that is also not the correct answer because we need the remainder 1. X is equal to 7. 7 into 7, 49. When divided by 12, remainder is 1 and even we need the remainder as 1. Hence, option C is correct. Next is, if the GCD of 101701 is 1, then the LCM is equal to what? One procedure is we can find the LCM. As the GCD is given to you, it means we have one option directly to find the LCM. In this case, we will apply one result which says that LCM of two numbers into GCD of two numbers is equal to the product of the given two numbers. LCM we need to calculate. GCD is given to us, that is 1. A is what? 101 and B is what? 701. Multiply this and hence we have D option. Next is, which of the following is a prime number? Whenever we have a question about to predict whether it is a prime or not, we will again use a result. We have a given numbers. We will take the square root of these numbers, find the approximate value, then find all the prime that is less than equal to that number. Like in this case, first case, root of 217. This is approximately is equal to 14.73. It means we need to find all the prime that is less than 14. The prime that is less than 14 is 2, 3, 5, 7, 11 and 13. Similarly, calculate what is the square root of 227. This is near to the 15 point something. And same for the other, the square root of these number is near to the 15. And in all the cases, we are getting a prime that is 2, 3, 5, 7, 11, 13 as they are less than equal to 14 and 15. Now check whether 2 divides this number. No. Whether 3 divides 217? No. 5 divides 217? No. Whether 7 divides 217? Yes. So hence it is not a prime number. If any one of them divides the given number, that means it is a composite number. So we can discard this option. Check for the second case. Whether 2 divides 227? No. Whether 3 divides 227? Clearly not. 5? Not. 7? No. 11? No. 13? No. So none of these number is dividing 227. It means it is a clearly prime number.